Okay, let's jump right in. We're going on a journey today, from the tangible waves you can actually feel and hear, all the way into the totally invisible, fascinating world of light and magnetism. Welcome to our Grade 8 Physical Science Explainer on waves and electromagnetic radiation. Whether you're just watching ocean swells roll up onto the beach, or you're simply heating up some leftovers in the microwave, you are interacting with waves. So today, we're going to unpack exactly how they work.
Here is our roadmap for today. We'll start with the anatomy of a wave, move on to sound in different media, and then tackle the electromagnetic spectrum. After that, we'll look at bouncing and bending light, jump into magnetism and electric fields, and finally wrap it all up with a quick recap and a transfer question.
All right, let's kick things off with Section 1, Anatomy of a Wave.
So fundamentally, a wave is just a disturbance. It's transmitting energy from one place to another, not actual matter. And we measure this using two main things, wavelength and amplitude. Wavelength is exactly what it sounds like, the distance between adjacent identical parts of a wave. Think crest to crest. Amplitude, on the other hand, is the distance from its normal resting position to its maximum displacement. So picture a seagull just bobbing out on the ocean. The wave's disturbance is moving forward across that wavelength, right? But the seagull itself just rides the amplitude up and down. That bird isn't being pushed across the ocean. It's simply experiencing the energy passing through the water under it.
Now, let's talk about the difference between frequency and period, because they are intrinsically tied together, just inversely. Frequency is the number of waves passing a specific point every single second. We measure that in hertz. Period, though, is the actual time it takes for just one full wave cycle to complete itself. So, because they are total inverses of each other, mathematically, frequency equals 1 divided by the period. The bottom line here, a higher frequency automatically means you have a shorter period.
And that brings us to the mathematical engine that literally governs all waves. Wave velocity equals frequency times wavelength. It doesn't matter if we're talking about ocean waves, sound, or light, this equation holds true. What this means in practice is that if the speed of a wave stays constant in a certain medium, cranking up the frequency means you get a shorter wavelength, and vice versa. It's a perfect, totally predictable balancing act.
Okay, moving right along to Section 2, Sound in Different Media.
So, sound is a mechanical wave, and what that means is it absolutely requires a physical medium to travel through. It needs stuff. Which brings us to our first pause check. Based on what you know about wave media, which material do you think transmits sound waves faster? Are we talking about a highly dense, rigid material like solid steel, or a light, easily compressible gas like the air we're breathing right now? Take a second and lock in your guess.
All right, got your answer? It's steel. Let's break down why. Sound is a longitudinal wave, which means it's made of compressions and rarefactions. Because the particles in a rigid solid like steel are just incredibly tightly packed and highly resistant to being compressed, they bounce back instantly. This transmits those vibrations super fast. To put that into perspective, the speed of sound in the air around us is roughly 331 meters per second. But in steel, it rockets all the way up to 5,960 meters per second. Not even close.
Let's pivot a bit and dive into Section 3, the electromagnetic spectrum.
Unlike sound, electromagnetic waves do not need a medium. They can travel through the absolute emptiness of a vacuum, like the vast space between the sun and the earth. And what's wild is that all different types of this radiation travel at the exact same speed, the speed of light. They just have entirely different real-world applications depending on their frequency and wavelength. Down at the low-frequency, long wavelength end, you've got radio waves carrying your AM and FM broadcasts. Bump up the frequency and energy a bit, and you hit microwaves, which literally rotate water molecules to heat up your food. Right smack in the middle is this super narrow band of visible light. That's what you're using to see and what plants use for photosynthesis. Keep cranking up that frequency and energy, and you eventually hit X-rays. Their wavelengths are so incredibly short they can pass right through human soft tissue to image broken bones.
All right, on to Section 4, Bouncing and Bending Light.
Because light travels in perfectly straight lines, we call them rays, its interactions with surfaces follow some really specific geometric rules. First up is the law of reflection. When a light ray strikes a beautifully smooth surface, like a mirror, the angle of reflection exactly equals the angle of incidence. Basically, it bounces off at the exact same angle it came in at. This perfectly organized bouncing is known as specular reflection, and it's exactly what lets our brains trace those rays backward to perceive crisp, clear, virtual images when we look in a mirror.
Which brings us to our second pause check.
Imagine a light ray passes at an angle from a fast medium, like air, into a slower medium, like water. What happens to its path? Does it just keep going perfectly straight, or does something else happen to it because of that sudden change in speed? It bends! This whole process is called refraction. Think of it like pushing a lawnmower from a smooth, fast sidewalk at an angle straight into thick, slow grass. That front wheel hitting the grass first slows down, which pulls and bends the lawnmower's entire path inward. Light does the exact same thing. When it hits that denser water boundary and slows down, the ray refracts. It bends inward toward the normal, perpendicular line. This is exactly why a pencil looks magically bent or broken when you stick it into a glass of water.
Next up, Section 5, Magnetism and Electric Fields. So we've seen what electromagnetic waves can do, but what's actually creating them? How does the electro part connect to the magnetic part? Well, it all ties together beautifully. See, a stationary electric charge has an electric field, but the moment those electric charges start moving, like in a current, they generate perpendicular magnetic fields. And when that electric charge oscillates, moving back and forth really rapidly, it creates these shifting, interlocking electric and magnetic fields that launch outward. That right there is an electromagnetic wave. Plus, on a physical level, inside ferromagnetic materials like iron, you have these microscopic magnetic regions called domains. When those tiny atomic magnets all point in the exact same direction, the entire piece of iron becomes a permanent magnet with a north and a south pole.
And finally, Section 6, Recap and Transfer Question.
Okay, let's lock in everything we've talked about today. We have covered a ton of ground, from physical vibrations to the literal speed of light. Notice how both types of waves actually share the same underlying mathematical rules, even though they interact with the universe in completely different ways. Mechanical waves, like sound, desperately need a physical medium because they're born from vibrating matter. Electromagnetic waves, though, are born from oscillating electric charges, so they are perfectly happy cruising through a complete vacuum. But both obey the fundamental wave equation, where velocity equals frequency times wavelength, and both can experience reflection.
So I'm going to leave you with this final transfer question to ponder. Think hard about what requires a medium and what doesn't. If a distant satellite suddenly exploded in the complete total vacuum of space, what would an astronaut floating nearby actually experience? Well, they would absolutely see the blinding flash of light because electromagnetic waves travel effortlessly through a vacuum. But they would never, ever hear the boom. Mechanical sound waves simply cannot exist without a physical medium to travel through. Space is completely, eerily silent. But if that's true, how do astronauts actually talk to each other on spacewalks? I'll let you chew on that one. Thanks for joining me on this explainer, and keep questioning the science around you.